Hi everybody, I'm Phil. I work on something called WebKit, which is a web browser rendering engine. Specifically, I'm one of the JIT compiler people for JavaScript. And what I want to talk to you about is using an exploratory project we have going on to use LLVM as a compiler backend for WebKit's JavaScript engine. So first what I'm going to do is I'm going to show you what a JavaScript engine, or at least our JavaScript engine, looks like. Then I'll tell you about the things that need to change in LLVM in order to make all of this work. So here's what our JavaScript engine looks like right now. There are 3 different execution engines, and we pick which execution engine we're going to use for JavaScript code on a per function basis. And the reason for that is there's a lot of run once code for which you don't want to invoke an optimizing compiler. That's where an interpreter comes in. We have an optimizing JIT for code that runs long enough where invoking an optimizing JIT is profitable. It's a payoff. And then we have what we call a baseline JIT, which is a JIT that's optimized for completely crazy polymorphic code. So if you've got stuff that's executing frequently, but it's doing like eval and other JavaScript crazy, then the baseline JIT is where you're likely to end up. And these arrows with OSR, that's on-stack replacement. So this is something that I'm going to get to in a couple of slides here. We actually will transition code from running in different engines on a per function basis, and we may do it while the function is currently executing. So you can sort of jump from the inside of a function while it's on the stack. So what we're basically trying to do here is introduce a 4th tier, which is if a function's been running even longer and now you're at the point where spending 10, 20 milliseconds to compile it is going to be a payoff, then we're going to on-stack replace from our current optimizing JIT into code compiled by the LLVM JIT. So that sounds great. So sort of interesting to look at what the actual goals and non-goals are. So the goal here is to generate fast code. We don't really care about LLVM compile times and memory usage as much. We're only going to invoke LLVM for the hottest of code. And we're not aiming at any particular kind of idiomatic JavaScript. The goal is that if you write a JavaScript function and it runs long enough, it will get LLVM compiled, even if it has massive amounts of crazy in it. Now, in order to do that, you actually need some features from LLVM that LLVM doesn't currently have, which makes this a particularly fun project and why this isn't just like an overnight weekend hack job where you turn it on and it just works. So the first thing that you're going to need is de-optimization, so the ability to go from to perform type speculations where even though the JavaScript language tells you nothing about the type of a value and you have an addition, say, and in JavaScript an addition could be anything from an integer addition, a double addition, a string concatenation, a method call, multiple method calls, loops, I don't know, hash table lookups. So you need to have a way of speculating of what's going to happen. And if you don't get the answer that you were expecting, you don't want the optimized code to have to deal with that because it pollutes your data flow. So what you want to be able to do is have bailout points, lots and lots of bailout points where the optimized code says, screw it, I give up on life. Here's where I left off. Now go execute this in an interpreter instead. So that's a classic technique in optimizing VMs. Like it's the reason why Java is fast. It's the reason why virtual calls in Java didn't matter in the end, because you can just de-optimize and speculate. The other thing you need is inline caches. So there are going to be certain places where the code is doing so much crazy that the best way to deal with it is by having the compiler do self-modifying code. So you just go in and keep modifying. The program will change its mind about what offset some field is at. So you say, okay, no problem. I'm just going to change the offset in the code, not recompile the whole thing. And then, shockingly, you actually need LLVM to support notions of stronger typing, because what happens is, since we have all of this machinery to do all this speculation, in the end, we're speculating so hard for certain pieces of code that we have more type information than you would get from C or C++. Some of this stuff has been proposed on mailing list, and some of it's already been landed. So I just want to talk about these a little bit. So for de-optimization, we're using this thing called stack map. That intrinsic is in the tree, and WebKit has an experimental feature already using it. We can already de-optimize, which I think is really cool. If someone had told me 5 years ago that a C compiler was going to support de-optimization, that it could actually work, I would have told them they're insane. But it actually does work. So yeah, lots of hard work by a bunch of people to make that happen. And then inline caches, that's the patch point intrinsic, and I'll go into that in a little bit more detail. And then stronger typing, I've said some things about them on the mailing list about TBA on calls. I won't go into that in any more detail right now. So inline caches, what the hell are those? So consider this simple looking statement. In an ordinary language, this would be like one instruction. But am I like completely out of time now? Okay. Well, let me just show you. I'll just try to go really quickly. So in JavaScript, this could be a simple heap access, or it could be a loop that loops over a linked list and does hash table lookups while potentially making method calls that could clobber the world. So the way that we support this is something called an inline cache. For the common case, it is a direct access. And the code that we emit compares the header of the object to 0x diet beef, and then jumps slow. No object will have a header that says diet beef, so you always jump slow. And then we do a load at offset 8 and a load at offset 0. And the point is the slow path observes what the object looks like, figures out its type, and let's say it's type number 42, overwrites diet beef with 42, and then changes the first thing to be an addition instead of a load, and the second thing to be a load at offset 8, for example. So this handles one object shape where you have a field directly inside of the object. Here, let's say type number 53, we do 2 loads. So this is for a different object shape where you have to do 2 loads, and so on and so forth. And it might even replace it with a jump to just a stub. So this is self-modifying code with arbitrary effects, and it's absolutely essential for performance. You can't run JavaScript without it. So this is what a patch point is, and I'll just stop talking because I'm already like twice over time. All right, thanks everybody. If you want to know more about patch point, come talk to me later.